Solutions today, and that's a pretty important concept to understand. We talked about this a little bit in the introduction of what a solution is. We talked about homogeneity and heterogeneity, and today we'll delve into what solutions are and why they're important. And just as a reminder, solutions are homogeneous mixtures. And by homogeneous, you can see here in the picture on the right with the green and the purple, it's going to be evenly spaced. So the purple is evenly spaced throughout the green. This is heterogeneous, meaning that some areas may have more green than purple. Some areas will have a whole lot of green and purple. Some areas will have no green and purple. For a homogeneous mixture, no matter where you look, you will always find the same concentration of purple in green or green and purple. The same numbers will always show up. It's sort of like if you flip a fair coin, you'll always get 50-50 heads or tails. No matter what you do, if you do it on Mars or if you do it in Zimbabwe, you'll always get 50-50 heads or tails if it's a fair coin. That same idea applies to homogeneity. It's going to have the exact same proportions, the same probability of getting what you want, no matter how you sample it and where you look. And these things do not separate. So if you look at a solution, it will not separate into whatever you mixed. If you mixed A and B together and they formed a solution, you can't just easily separate A and B out. You can't just go with your hand and pick out A. They're entrenched in one another. They are not, though, chemically reacted. It's still a physical change. I am mixing two things. Mixing is a physical change, not a chemical change. And they act the same throughout because they look the same throughout. Now we call water-based solutions aqueous solutions. Aqueous from the root for it is water. I want to again stress the idea of heterogeneous mixtures. We talked about that in the introduction a little bit. Here, these beautiful solutions here, these are actual solutions, aqueous solutions. They are homogeneous. This is an example of a heterogeneous mixture, and this would be an emulsion of fat in water and what we commonly call milk. And if you look at milk, at first it may look pretty homogeneous. It isn't. It's just pseudo-homogeneous. If you leave milk alone for a while, it will separate into fat and water. You can also induce this change by adding stuff to milk. So if you want to go home and see that for yourself, go home and add some salt to your milk and you'll see it separate quickly. Or add some vinegar to your milk, and some recipes actually call for that to create that. So when you do that, you're destabilizing this non-solution. It's not a solution, and you're forming what you separate that. Left to its own volition, any heterogeneous mixture will separate. Aqueous solutions do not separate ever. They will separate only if you put some work into it. Otherwise, they will stay as is forever. So this red solution here will stay this red solution here unless you evaporate the water or something, unless you put some work into it. But if you just keep it as is without any physical change, it will stay like that. Milk will not. It will separate over time. It is unstable. It is what we call metastable. Now let's look a little bit about the dynamics of solutions, and I have a few pictures here to show you. I have NaCl, that's a classic ionic compound. When I throw that in water, I will form a solution. So salt water is indeed a solution. You can't easily separate the salt out. You have to drive off the water to get the salt back out. If you leave it by itself, it will always be a solution of salt water, and that's why, for example, oceans, they have salt stuck, quote unquote, stuck in there. The salt is not going to go to the top or to the bottom. The amount of salt is going to be uniform throughout a specific area. If you were to make salt solutions at home in a cup, right, no matter where you put a straw through to that in that cup, it will taste just as salty because it's going to have the same amount of salt per water no matter where it is in the cup. Okay, When the NaCl molecule goes into water, what happens is that the Na plus ion and the Cl minus ion actually separate, and water molecules kind of huddle around. And what this is called a solvation. They solvate the ions like that. They stabilize them because they're polar molecules, and so the positive portion of the water molecules, the hydrogens, will align next to the Cl minuses because they're attracted to one another, and the oxygen, which is the negative side of the water molecule, the red stuff here, will attract itself to the Na plus, and they will effectively separate the Na plus and the Cl minus from one another. They will solvate them. All right, and the to look at it again, if it's a molecule that's not ionic, like sugar, sugar will not get solvated in this manner. It will still get huddled around with more water molecules, but it will not separate into anything because there's nothing to separate sugar into. Okay, so they do not dissociate. Molecular solutions do not dissociate. They are still solvated. They're not dissociated in the water. Ionic solutions will separate the cation and ions. Here's another clear, more high-res picture of that. A sugar solution here. The sugar is this agglomerate of red and white balls here, which are typically it's got hydrogens and carbons and oxygens here, and the water molecules do huddle around that. You see that, but the sugar molecule itself does not separate into any specific moieties. The ionic compound, this is not necessarily sodium chloride, but it's some sort of a binary compound. The pluses and the minuses separate, and the water huddles around the pluses and around the minuses separately, and effectively separates the two. And that's what we call dissolution of an ionic compound. They dissociate in water. Okay, so it's just to show you what happens microscopically. It doesn't change much. Solutions are solutions are solutions. It's just that ionic compounds do tend to have these charges around, which lend themselves to a lot of other important features of solution chemistry if you're dealing with ionic compounds. Things like electricity. Electricity can be conducted through an ionic solution, and it cannot be conducted through a sugar solution because there's no charges separated there. Okay, we'll talk about that more. And so, to denote this dissolution, okay, we will put this AQ after the compound. So far we've done S for solid, L for liquid, G for gas. Now I'm introducing this fourth thing, AQ, and all that, it just means aqueous. So that just means they got dissociated. So if I have NaCl and I put AQ on, right after that, that means if you see this thing without the arrow, just this, imagine you're just seeing NaCl, AQ. That means that should tell you right away that this is in water. NaCl got stuck in water, it got stuck in water, and now it's separated into Na plus and Cl minus. This is effectively what happens. But if I were to write NaCl with an S afterwards, that would mean that it's a solid, not in water. If I put AQ, that means that it is dissolved in water. All right. Oops. And the properties of solutions, again, if the solvent evaporates, the solute is recovered as a solid. Now, what is this solvent solute again? To remind you, the solute is whatever is present in the lesser amount, and the solvent is whatever is present in a larger amount. And aqueous solutions, the solvent is always water. The solute is whatever you're putting in the water. So if I am putting NaCl in my water, NaCl is my solute, water is my solvent. If I evaporate my water, my solvent, I will recover my solute, my NaCl. Okay? The amount of NaCl I can throw in water is dependent on the temperature. Okay? If I increase the temperature, I can put more stuff in it typically. So, for example, if you go home and you can do this yourself, you put a ton of sugar in water and you mix, okay? Some of the sugar won't dissolve if you put a ton of sugar. What you would do then is you pour the water that does have the sugar in it, okay? Pour it out into another cup, okay? Leave that solid behind. Now in the second cup now you have a lot of sugar in your solvent. All right, at the maximum amount you can put. Okay, if you put any more, it will just fall to the bottom. If you took that cup and put that in the fridge, all right, the amount of sugar in the cup the amount of sugar would stay the same. The capacity of the water to hold sugar will reduce in colder temperature, and you will see some sugar come out. Okay. Uh, Conversely, if you were to take that same cup and put that into a pot and heat it up, you can add more sugar. The capacity of the solvent to dissolve stuff changes with temperature. All right, and that also works with weather. I can call air a solvent. Why not? Right, and I can call water a solute. Why not? If I have a lot of air, which I do outside, and I have a little bit of water, which I do outside, typically there's not a lot of water in the air, even though it feels like it here in Florida. It's fairly small. The amount is fairly small because we do need about 21% of the air to be oxygen for us to breathe. It does not rival that even in the slightest. It's a fraction of that. So it's a tiny microscopic amount of water in the air. And so air functions as a solvent in this case, and water functions as a solute. It is homogeneous in the sense that throughout this town, if it's whatever percent humidity, it's going to be about that percent humidity no matter where you walk around. It's about homogeneous. And so what happens is if the temperature suddenly drops as the weather fickly does that, the capacity of air to hold water will reduce, and then water will come out, just like the sugar would come out. Water would come out, and the water comes out as a liquid on surfaces around, and that liquid we call dew. And that's basically all that dew is. It's basically a solution that cannot hold as much. The temperature changed, now it can't hold as much as it used to, and it precipitates out and forms dew. Okay. Solutions, additionally towards being temperature dependent, they're also electrically neutral. So whatever positive I have negative to offset the positive. All right. So enough about that. Let's talk about solubility.